So our today's speaker is Olivier Benoist, and he will tell us about abstractions to rationality over algebraic non-closed fields and intermediate Jacobians and things.
Yes, thank you very much for the introduction and for the invitation. It's a pleasure to be here. I will talk about the joint work with Olivier Wittenberg, whose topic I will now explain. So in the whole talk, I will fix a field K, and I will consider over K a variety X that is smooth and projective. And the question will be, the goal is to decide whether X is rational over the field K, and meaning birational to projective space over K. So I will first start by explaining that in dimension 1 and 2, this question, the answer to this question is fully known. So if the dimension of X is 1, first you consider the case of an algebraically closed field, and the variety X is K rational if and only if, well, for instance, it has genus 0, so it has no one forms. And my variety is geometrically connected. And if you look at a general field, then X is going to be K rational. So the first thing you do is you go to the algebraic closure and you decide over the algebraic closure of K whether it is K rational or not. And this you can do by the previous step. So the first condition is that X be K bar rational. And that tells you that X is a conic, and a conic is K rational if and only if it has a point. So there is a second condition that X should have a point. So this is very classical and solves the problem in dimension 1. In dimension 2, I'm going to do the same. First, I consider the case of an algebraically closed field. And then my variety is K rational if and only if, by Castelnuovo's rationality criterion, there are no one forms on X, and there are also no sections of the second power of the canonical bundle. Okay. And over a general field K, what do you do to decide if the variety X is K rational? So since we're looking at surfaces, we are looking in birational questions, we may always assume that K is actually minimal over K as a surface. So I assume that my surface is minimal. And then for X to be rational, a necessary condition is that it is rational over the algebraic closure. And this is something that I can decide using Castelnuovo's criterion. Then there is the condition, as in the curve case, that X should have a rational point. And it turns out that for surfaces, there is a third numerical condition that the self-intersection of the canonical bundle should be at least 5. And it is a deep and difficult theorem due to many people. So I'm going to quote the main participants that are Segre, Manin, and Исковских. That this is a necessary and sufficient condition. So this entirely solves the problem of rationality over all fields for curves and surfaces. And in this talk, I will consider what happens in the next possible dimension. That is the case of 3 folds. So over the complex numbers first, one of the main techniques used to study rationality of threefolds is the Clemens-Griffith method. So how does it work? To the variety x, one may associate a variety that in the talk I will denote by a of x, that you can define in a transcendental way. So using Hodge theory. So what is it? It's a principally polarized abelian variety over C, which is called the intermediate Jacobian of X. And it has the property that when X is rational, it is isomorphic as a principally polarized abelian variety to the Jacobian of a curve. So, which is iso as a principally polarized abelian variety to the Jacobian of a smooth projective curve.
But maybe reducible, right?
Yes, the curve might not be connected, which corresponds to the case where it is the product of Jacobians of smooth projective connected curves. Absolutely. But yeah. Okay, and the original application of this point of view, so this gives obstructions to rationality, and the original application due to Clemens and Griffith is the fact that smooth cubic threefolds are not rational. And this theorem of Clemens and Griffith, this strategy has been applied as well over any algebraically closed field by Moore with the same result. So what I will want to do today is consider the case of a general field to explain how to apply over a general field the method of Clemens and Griffith. So as in the curve case and the surface case, I assume that we have solved the rationality problem over the algebraic closure. And so I restrict myself to the case where X is K-bar rational, is rational over the algebraic closure. If not, then X is not even K-rational. And what I will do is associate to X variety A of X, which is a principally polarized abelian variety over the field K. And I will not define it now. It's going to be defined later in the talk. And it will have, as in the Clemens-Griffith situation, the property that it is a Jacobian if the threefold X is K-rational. And okay, so the idea, the basic, the starting point of our work is the idea that, of course, since my threefold X is rational over the algebraic closure of K, if I look at this principal, yes? If I look at this principally polarized abelian variety over the algebraic closure, it is a Jacobian. But there is no reason why A of X itself over the base field should be a Jacobian. And this may give obstructions to the rationality of X over the base field even if X is k-bar rational. And I'm going to now just state the first theorem that is a concrete example where this precise obstruction occurs. So since I'm going to write down equation, I will assume that the characteristic of K is not 2, but you can write down examples in characteristic 2 if you want. I will assume the existence of an element in K that is not a square. That's not what I wanted to write. And then I claim that the variety with equation s square minus alpha t square is equal to x4 plus y4 plus 1. So it is an affine model of a smooth projective variety. Is so rational over k adjoint square root of alpha. It is unirational over the base field, but it is not rational over the base field. And so in particular, if you combine the last two statements, it is what people call a counterexample to Lurot, to the Lurot problem. It is an example of a variety that is unirational but not rational. And the difficult part in this theorem is to prove that X is not K-rational, and it is exactly what I told you. Its intermediate Jacobian A of X is not the Jacobian of a curve over the field K. Okay. So this was the starting point. And then Hassett and Schinkel realized two things. The first is that there are finer obstructions.
Sorry, and just a question about the example. So if you add the square root of alpha, then the conic bundle just stops being minimal, stops being standard, right?
Absolutely. Yes, the assumption that the variety is rational over, yes, absolutely. Absolutely. It becomes a conic bundle over P2 with a section, and so it is rational.
Thank you. Thank you.
Is it okay?
Yeah, totally clear.
So Hassett and Schinkel have noticed that there are finer obstructions to K rationality. No, that was bad. I'm sorry.
Something happened.
Okay, so I accidentally erased everything, but I hope it's going to be all right. So Hassett and Schinkel notice that there are finer obstructions to K rationality that occur by looking not at the intermediate Jacobian itself, but at torsors under this intermediate Jacobian. And they also noticed that these obstructions apply very well to threefolds that are constructed as complete intersections of two quadrics in 5-dimensional projective space. And what we do is that we make these ideas work over any field K. And the main theorem in this direction is the following. So I take X over K, a smooth, complete intersection of two quadrics in 5-dimensional projective space over K, then X is K rational if and only if it contains a line defined over K.
Sorry, and can you repeat once again? So you work over any field K and Hasse-Chinkel, what was the restriction for the field?
Okay, so their first work is over the real numbers, where they introduced these two new ideas, and they have a second paper over subfields of C.
I see.
The statement solves the conjecture of Kuznetsov and Prokhorov. We learned from them that it was a reasonable statement to consider. It is a crazy looking statement. We learned from them that it is reasonable. And in Kuznetsov and Prokhorov apply the same ideas. To other classes of varieties, so to several other classes of Fano threefolds, not only complete intersections of two quadrics. Okay, so now, moreover, for these varieties, smooth complete intersections of two quadrics, the unirationality problem is also entirely solved. So I'm going to state it as theorem 3. So now it should be attributed to many people. So of course, Manin to start with, and then Kolyotelen, Sansuk, and Swinnerton-Dyer, and us for the generality in which I state the theorem. So I take X over K as in theorem 2, meaning a smooth complete intersection of two quadrics, say of dimension 3. And then X is K unirational if and only if it contains a point. So it is very striking that for this class of variety, you can decide unirationality by looking if the variety has a point, and you can decide rationality by looking if the variety has a line. And so combining these two explicit description of rationality and unirationality of these varieties, we construct new counterexamples to the Lurod problem. So, okay, I'm going to state it as a theorem 4, but it's really an application of the two previous theorems. So you fix an algebraically closed field, and then I claim that there exists a variety X as above over the field F double parenthesis T. So as above, meaning smooth complete intersection of two quadrics in P5. And that is, so rational if you add a square root of T. That is unirational over the base field, but that is not rational over the base field. And this example is particularly interesting for the following reason. in characteristic 2, it is the first example of X that has the following properties. So that has a point that is rational after a purely inseparable extension of the base field. So that is, if you want, rational over the perfect closure of K, but not rational over K. And it is in some sense the simplest such examples, because there are no examples in dimension 1 and 2 by the complete understanding we have of rationality problems in dimension 1 and 2. So no such example. In dimension 1 or 2. Okay, so rationality may vary under purely inseparable extension of the base field. Okay, so this is all the theorems I wanted to state. The goal now is to explain the technique more precisely. So I need to define what the intermediate Jacobian is and precisely what are the obstructions to rationality that it gives. So I turn to discussing the intermediate Jacobian. So I work in the setting that is interesting for rationality over base fields. So X is smooth, projective, of dimension 3, because this is the dimension where the Clemens-Griffith method applies. And K bar rational, because I assume that the rationality problem is already solved over the algebraic closure.
Olivier, and can I ask a question about the previous slide?
Yes.
You say that there is no such perfectization effect in dimension 2.
Yes.
So you just use this criterion with the minimal surface, or do you claim it only about rationality or about arbitrary birational equivalence?
Oh,
Suppose that I have two surfaces which are defined over a field and become birationally equivalent over some inseparable extension.
So here, there is something here that is, I need a point. That is, it's possible that you're rational over a purely inseparable extension, but you do not even have a point over the base field. And then, of course, you're not rational.
Yeah, fair enough.
So you need to ask at least that your two, and so I didn't think about your question, and so you take, say, two smooth projective surfaces, say both with a rational point. I would need to think. I didn't think about.
After life becomes perfect, they become birational equivalent. But so can they be not birational equivalent before? Well, anyway, anyway, so the green comment relies on rationality criteria. So it's about rationality, not arbitrary birational equivalence.
No, yeah. The green comment is about rationality, and actually, I didn't think explicitly about the question you're asking.
Thank you.
Okay, so now I was discussing what the intermediate Jacobian is. So over the field of complex number, I have already explained that there is a transcendental construction that is the classical intermediate Jacobian. And what is useful to know, and that is used to define intermediate Jacobians more generally is that there is an Abel-Jacobi map that sends codimension 2 cycles that are algebraically trivial, well, to the complex points of the intermediate Jacobian, and that this Abel-Jacobi map is an isomorphism. So you can really think of the Cho group of codimension 2 cycles that are algebraically trivial as a replacement of the intermediate Jacobian. And it is this point of view that allows for construction over more fields. So that was done by Moore over algebraically closed field. What Moore does, he defines the intermediate Jacobian to be universal in some precise sense that I'm not going to state with such an Abel-Jacobi map. So with such a map. Okay. If K is a perfect field.
With C replaced by K, right?
Exactly, exactly. With exactly, absolutely. Thank you. Yeah, I should have put K here. Ah, thank you. So if the field K is perfect, then Aschter, Casalina Martin, and Vial have noticed that thanks to the universal property of Moore's Jacobian, the Galois group of K acts naturally well on the intermediate Jacobian of X over K bar constructed by Moore. And this shows that this intermediate Jacobian descends to an abelian variety that I still denote by A of X over K. And this is the correct intermediate Jacobian over the base field K. If K is general, so not necessarily perfect, this approach fails. Moore's definition is too Moore's definition does not allow to descend the intermediate Jacobian to K. And the reason is the following. So you would want to apply descent from K bar to K, but to do so, you would need to be able to compute the points of the intermediate Jacobian with values in Artinian rings, say K bar bracket epsilon, with epsilon square is equal to 0. And you would need to compute that to know that. And Moore's definition does not allow you to, does not give control on these, on the points of the intermediate Jacobian with values in arbitrary rings, in particular, not in Artinian rings. And so you can't formally use Moore's definition. And I mean, this problem gives rise to the solution, which is, well, to define the intermediate Jacobian over an arbitrary field, write down the functor that it should represent. And that's what we do. So, and look at what we want. We want to construct a variety whose points over an algebraically closed field are in bijection with some codimension 2 cycles. So the problem we want to solve is the analog for codimension 2 cycles of the theory of the Picard scheme that is concerned with codimension 1 cycles. So the solution to this difficulty is inspired by the theory of Picard schemes. So we wrote down a functor so that we denote by cho ch2x over k, which really should be thought of as an analog for codimension 2 cycles of the Picard functor. And and it's contravariant, and it sends a scheme over K to an abelian group, to abelian groups. So this functor I'm not going to define right now. I will do it later. And we prove the following. So, I'm going to write now what should maybe be thought of as the main theorem of the talk. It is the list of properties of this functor that shows that it indeed plays the role of an intermediate Jacobian. So first, it is representable. So show the x over k is represented by a group scheme locally of finite type over k. Okay, then I can look at its connected component of identity. So and the quotient is the group of connected component of this group scheme that I denote by Néron-Sévéry 2x over k. And the claim in the assertion number 2 is that this connected component over k is an abelian variety. And it is this abelian variety that I want to consider as the intermediate Jacobian of x. And that I will denote, if I want, by A of x. It is the one that we use for rationality problems. And an advantage of this point of view of having this whole scheme that is bigger than just the intermediate Jacobian is that built in are the torsors under the abelian varieties that are useful for rationality problems in a Hassett and Schinkel point of view. So, for instance, if you denote delta this map, and if you have a k point of the Néron-Sévéry group, the inverse image of alpha by delta is a torsor under the intermediate Jacobian. And we will find obstructions to rationality of x also in these torsors. Okay.
Sorry, can you remind what's the setup? Now you're working with arbitrary threefold, right?
So yes, maybe I should recall. So x over k is smooth, projective, k bar rational, threefold.
Thank you. And do you really use k bar rationality here somewhere?
Yes, absolutely and definitely. So
not just k bar rational connectedness, but really.
No. We very much use K bar rational, and we use it in the proof of 1 for representability. We use it in an essential way. So it would be very interesting to prove representability of our functor under more general hypothesis. So for instance, for Fano threefolds, as you say, and we did not do that. We did not try actually. One point is that, it is our proof of rationality that is particular to K bar rational threefolds that also leads to the obstructions to K rationality, because we have to analyze K rational threefolds to get obstructions to K rationality. So our proof of the obstructions to K rationality that I will state later also shows representability in the case of K bar rational threefolds. So this is the reason why we stick to this setting. But it would be interesting, and we didn't try to construct this group scheme for more X.
And can you hint, so what kind of strong property you get from rationality that you use for assertion 1?
Like a birational map to P3 over the algebraic closure. I will explain the idea of the proof. It will be very clear that yes, more if X is K rational, which we reduce to, then X is built from P3 by blowing up curves, and we can prove representability by looking at what happens when you blow up a curve.
I see.
Yeah. But yes. Are there other questions?
Maybe
probably you also prove that if you extend scalars to K bar, you get the Morris Jacobian, right?
Absolutely. Yes. So we retrieve, I will not state it, but we retrieve exactly Morris Jacobian over the algebraic closure, and Ashter, Casalaina-Martin, and Vial's Jacobian over a perfect field. Absolutely. And even in this case, so we do not have new applications even in these cases, our point of view may be interesting because, for instance, this theorem, what it does over, say, an algebraically closed field, it computes the functor of points of Morris intermediate Jacobian. For instance, it computes its tangent space. And this may be useful for other purposes. To know, to have Morris Jacobian defined not only by a universal property, but by its whole functor of points. Are there other questions? Okay, I continue to state the theorem. The third assertion is about what you get if you take, K bar points. Well, the K bar points of our group scheme is just the Cho group of X K bar. So our group scheme really parameterizes codimension 2 cycles on over the algebraic closure. Really as the Picard scheme does for codimension 1 cycles. And inside it, the identity component corresponds to cycles that are algebraically trivial. And the quotient is really the Néron-Severi group of codimension 2 cycle. If you take K bar points, you take a group of finite type. Because it's a Néron-Severi group, exactly as for in the theory of Picard schemes. For rationality problems, we need to have more than just an intermediate Jacobian that is an abelian variety. We need a principal polarization on it. And so this is item 4. our intermediate Jacobian carries a canonical principal polarization let me call it theta x. Okay, so maybe I'm not going to, so okay. Okay, maybe I'm not going to say more about it. Okay. I could state a characterization of it, but I will not use it anyway. And so we construct a canonical principal polarization on our intermediate Jacobian, which is the one that we play the same role as the usual one on complex intermediate Jacobians. And the last assertion of this theorem is the one that will give rise to obstructions to K rationality. So it's item 5 of the theorem. It analyzes what happens if X is moreover K rational. And then there exists C over K, a smooth projective curve. And G over K group scheme. So that what I want to say is that, I mean, I'm writing our group scheme show 2 of X over K is a direct factor of the Picard scheme of C, of the Picard scheme of a curve. And it is a direct factor in a way that respects principal polarizations. So in the following sense, that if I restrict to identity components, well, there is a principal polarization on G0, such that this is an isomorphism of principally polarized abelian variety. So the obstruction to, should this be, yes, thank you very much. Thank you. Thank you, of course. Okay, sorry. Yes, absolutely. So you can, yeah, absolutely. So if X is K-rational, then it's show to X over K is a direct factor in a principally polarized way of the Picard group of the Picard scheme of a smooth curve, of a smooth projective curve. And okay, so this is the strongest obstruction to K rationality that we can formulate, the more general one that we can formulate in this setting. If you restrict to connected component of identity, you get the usual Clemens-Griffith obstruction that the intermediate Jacobian should be the Jacobian of a curve. But if you look at all the connected components of identity, you get obstructions, the ones that were considered by Hassett and Schinkel. And if you look at the group of connected components, you also get obstructions. Okay.
Olivier,
yes.
Is it correct that in characteristic 0, you don't need this group scheme G?
I mean, if in all characteristics, and if you only look at connected components of identity, you don't need the scheme G. if you only look at connected components of identity. But
does it mean that G0 is trivial?
Not necessarily. You may enlarge. What I don't think it is clear that you can make G0 trivial and have this statement. You need to take in. If you forget about what is green now, if you forget about this, then you can throw G away. Otherwise, I don't think you can throw G away, because you need to take into account the group of connected components. And I'm not.
Okay. And is there some geometric meaning for this group G0?
Not really. I don't think so. No. No. You mean the smallest possible? No. I think the property that comes out of the analysis of what happens when X is k-rational really is that our Cho2 X over K is a direct factor in a polarized sense of a Jacobian of a smooth projective curve. And it's not clear that you can simplify. It's not clear that you can simplify. Maybe you can simplify separately connected component of identity and group of connected components, but okay.
I mean, is it something like Zariski closure or something? Or?
No. It's no, but you will see how it will appear in the proof.
Okay.
You will see how it will appear in the proof.
Thanks.
I don't think I can state something simpler than what is on the screen.
I have a question about part 3. So the case of so if K is not algebraically closed, the case of the Picard scheme suggests that you should not get an isomorphism between the K points and the actual, Chow2 of X.
Absolutely.
But at least there's a short exact or an exact sequence that relates the two, up to some obstructions. Is there a similar situation here?
So the short answer is not that I know of, and what I know is that it is much more complicated than the theory of Picard scheme, and it has to do with for instance, for Picard scheme, if X has a K point, then it's true that the K points of the Picard scheme are indeed the line bundles on X, because of the exact sequence you mentioned. This is false for codimension 2 cycles, and the counterexample that has been constructed by Claire Voisin. It is the so-called lack of a universal codimension 2 cycle over the intermediate Jacobian, even over the complex numbers. So the codimension 2 cycles behave for this problem much worse than codimension 1 cycles. So I do not expect that there is a simple way to compute K points, even if X has a K point. And okay. I have nothing clever to say.
Okay, thank you.
Are there other questions? Okay, so now there are two. Okay, so the next thing to do, I think, is to give a definition of the functor, because I've stated all its properties. We see how it might be applied to rationality problems. It gives obstruction to rationality. This is point 5. Now I want to give a definition of it, at least for the theorem to make sense. So, definition. So the difficulty is that we want to we need a contravariant functor. So we need something that we can pull back. And in general, the Chow group of codimension 2 cycle, you can't pull it back by an arbitrary morphism if the varieties are not smooth, etc. And that's the reason why when you define the Picard functor, you don't use codimension 1 cycles, you use line bundles that you can always pull back. Whereas codimension 1 cycles, you can't always pull back. So here we are not going to use codimension 2 cycles that you can't pull back. And the idea is to use K-theory that you can pull back to build a functor. And how is K-theory going to be useful? That there is a link between K-theory and Chow groups that is given by a Chern character. So I want to write it over K bar. And this Chern character isomorphism. So here, K0 is really the Grothendieck group of vector bundles on xk bar. And we use this isomorphism to slice the Chow group of codimension 2 cycles inside K-theory. So that's the basic idea. There are, of course, two obvious difficulties to make this work. The first is that the Chern character isomorphism is only rational, not integral. And the second one is that, well, on the right-hand side, you have the whole Chow ring, not only the Chow group of codimension 2 cycles. So this is why you have to slice down K-theory a little bit. And this is what I'm going to do right now, maybe on the next page. I'm explaining how to recover the Chow group of codimension 2 cycles from K-theory. And I really start by doing it on xk bar. So if you look at the K-theory group of xk bar, there is a morphism that is given by rank of vector bundles and determinant of vector bundles that lands in Z times the Picard group. And you can consider the kernel of this morphism that I denote by SK0. Okay, so this is already a good thing. Really, taking the kernel of this morphism, it removes Z, that is the Chow group of codimension 0 cycles, and the Picard group, that is the Chow group of codimension 1 cycles. So only taking this kernel removes the Chow group of codimension 0 and 1 cycles that we didn't want. We still need to remove the Chow group of codimension 3 cycles to only retain codimension 2 cycles. And this is what I do now. Of course, we consider threefold, so codimension 3 cycles, they're points.
Maybe it makes sense to mention that the morphism is a split epimorphism.
Absolutely, absolutely. I agree. So codimension 3 cycles, they're points, and moreover, we're on rationally connected threefold, so all points are equivalent. So I really have to remove the class of a point, and it's very easy. I take any point, and I can consider its class, we call it new. its class in K theory. So really you take the structure sheaf of this point. So, okay, it's not a vector bundle, but you can resolve this sheaf using bivector bundles. So this gives rise to a class in K theory. And since it's supported on a point, it has trivial rank and determinant, and it indeed lives in SK0 of xk bar inside of K0. And to remove codimension 3 cycles, so you mod out by, so you consider because SK0 of xk bar modulo the subgroup generated by nu. Okay, now we've removed codimension 0, 1, and 3 cycles, or it only remains codimension 2 cycles, and this is actually the Chow group of codimension 2 cycles. And how does it work? There is a morphism, well-defined morphism to the Chow group of codimension 2 cycles on xk bar that is given. Yes?
Maybe it also makes sense to mention that this embedding of Z is a split monomorphism, and the splitting epimorphism is given by the Euler characteristic.
By the Euler, you're talking about the morphism from Z to K0?
I mean that there is a morphism in the opposite direction given by the Euler characteristic, such that the composition is the identity. Because of that.
Oh, yes, absolutely.
It's a direct cement.
Yes, you're right, absolutely.
So you could just from the whole beginning, just to add Euler characteristic to the rank and determinant, and just take the kernel.
Yes, I agree. But then I will want to do it in family to define functors. And so this is the reason why I proceed in this way. Because the presentation I give now over K bar will work over any base.
Yeah, but the Euler characteristic also makes sense in a relative setting. This is just, I mean, you take the derived push forward to the base.
Well, you will see, but
Okay,
I mean, for rank and determine, you will see how the definition of the functor looks like. And I'd rather write the co-kernel of a morphism from Z to it, because it will be quotient by the group scheme Z. You will see how the functor is defined. Maybe let's discuss them.
Sure.
So yeah. I agree that what happens over K bar is, I mean, not difficult. As Sasha points out, actually K0 is a direct sum of 4 pieces, and we are only interested in one of them, that is codimension 2 cycles. And okay, the last thing I need to say is that the second Chern class actually induces an isomorphism here. So we really retrieved the Chow group of codimension 2 cycles, and this is not a trivial fact. It is the so-called Riemann-Roch theorem without denominators, which is due to Joannolu. Okay. So this is what happens over K bar, and I'm going to mimic this procedure to build a functor. So in general, what do? You consider, so I'm going to start with a K theory functor that is very naive. What do? To a scheme over K, I associate an abelian group. And what do? To the scheme S, I associate the K0 of X times S, like we do for Picard functor, for instance. And of course, for absolutely general scheme S, I need to be cautious. I mean, I need to be careful about definition of K theory. I'm going to use perfect complexes for people who know. Okay. And I'm going to find my functor inside of K0 by the procedure I have described. So how does it work? So I look at the kernel of the morphism of functor rank determinant from K0x over K to the group scheme, the constant group scheme Z, that is the rank, and to the Picard functor pic x over K, that is the determinant. Okay, now there is one thing already in the theory of Picard scheme. We know that we have to get a functor that is representable, we have to sheafify the functor for FPPF topology or for étale topology at some point. So here I'm going to make now this sheafification, the functor that is written here, the kernel, which is a functor, I will sheafify it for FPPF cohomology. Oh. Okay. And now that it is sheafified for the FPPF cohomology, this functor now has a canonical K point that is the class of a point. That is the class that I denoted by nu. And so this class gives rise to a morphism from Z to this functor. So this is really, it sends 1 to the class of a point. And I take the co-kernel. So it looks like a complicated formula, but I've only done in family and with SPPF sheafification, what I explained in the last slide over K bar. Okay, so this is just the definition. And it is for this definition that the main theorem I stated holds. Are there questions? Okay, if there are no questions, my goal now is to explain the idea of the proof of the main theorem, how to show that this functor has the properties I claimed. So the first thing to notice that is a good news is that to show, the first 4 properties that were the general properties of this group scheme, representability, connected component of identities, and abelian variety, etc. One may replace the base field with a finite extension. And really, because if you're, for instance, if your group scheme is representable after a finite extension, then by FPPF descent, it was representable to start with over the base field. So this is really by FPPF descent. And this argument works because we have the whole functor. The FPPF descent didn't work with Murray's definition because he was unable with his definition to compute the whole functor. But since we prove a stronger statement that is computation of the whole functor of points, we can argue by FPPF descent. So we can extend the base field. And since our variety X was rational over the algebraic closure, we can assume after such an extension that it is rational over the base field. Okay. Okay. Now maybe, okay, maybe since I have a diagram, maybe I will go to the next slide. Now my threefold is K rational, and we will apply the strategy of Clemens and Griffith. So the precise, that is, look at the birational map to P3 and look at the curves this birational map blows up. So the precise statement we use is due to Abiancar, if K is perfect, or Cossard and Pilton in general. We have a diagram as follows. So there is a map like that. Let me call it F. It is birational. And yn plus 1 is obtained by a sequence of blow-up of P3 that I call Y1. Etc. So here, the map that I denote by pi I is a blow-up of a regular curve Ci inside Yi. Okay, so I wrote a curve. Of course, maybe you need to also blow up points, but this is easier to analyze. I ignore it just to simplify the talk. I ignore the fact that maybe you blow up points. Okay, 4 points. But I will pretend they're always curved just to simplify. And so we really have this tower of blowups of P3 and then a contraction to X. And to prove all the theorems you want about X, we will move up the tower of blowups and down to X. So first we start on P3. And you have to, on P3, to understand our functor in the case of P3. And this functor is very easy. I mean, you all know the Chow group of codimension 2 cycles on P3. You know it's isomorphic to Z. And in fact, there is this isomorphism of group schemes. And the proof is just that of this isomorphism as functors, really. You need to be able to compute K-theory of projective bundles. But this has been done by Grothendieck in SGA6. So now that we understand P3, we need to move up the tower of blowups. And but this is also well understood. There is an isomorphism of my group for yi plus 1 with the one at stage I times the Picard scheme of the curve that we blow up. And so this really looks like the formula for the Chow group of codimension 2 cycles on a blow up, right? And I mean, that this is an equality of functors, actually. You need a little bit more. You need to be able to compute the K-theory of a blow up. And this is a computation due to Thomason. So now we've moved up all the tower of blowups, and we have been able to compute the, say, the functor Chow2 for yn plus 1, and we need to go down to X. So how is that done? You want to compare the Chow group, the functor for X and the functor for yn plus 1. And there are two maps that relate the two, pull back and push forward by F. And these two maps satisfy that if you pull back first and then you push forward, you get identity, as you can expect. But this is not a trivial fact. It uses a non-trivial result due to Schatz-Matthew and Rühling. And this identity that pull back, push forward is the identity allows you to view SHO2 x over k as a direct factor of SHO2 yn plus 1 over k. So hence, what you've shown is that really SHO2 x over k times the group that is the kernel of F lower star is isomorphic to Z times the product of the Picard scheme of all the curves you've blown up. And okay, so SHO2 x over k is now a direct factor of a representable group schemes, and this implies easily representability.
And why do you have this extra Z?
Z was the SHO2 x over k for P3. You started with P3. And you start with P3, you blow up curves, and you arrive. And so the Z is SHO2 P3 over k.
Suppose you blow up something, not a P3. Could you say that the Jacobians are related the same way?
Yes, absolutely, absolutely. So indeed, you will be able to say something about these functors for two birational threefolds. Like the only point is that for something other than P3, we do not prove representability. You would have a statement about functors, but not about variety group schemes, just because we didn't prove representability. But if you do, then you will have statements about group schemes.
But do you need this threefold to be rationally connected? To understand what happens under blowups, no. But I mean to define SHO2.
Oh,
First step you have to chop out the point, right?
Yes, because of the class of a point. Yes. Yes. Yes, it would certainly, there are many open problems. Like, yeah, I agree. It's unclear in what generality it is reasonable to try to define a functor SHO2. We do not know what is the precise definition we give is so may apply to all rationally connected threefolds. It has the advantage that we can, since K-theory is very well developed, we can prove all that we want in this case, but it might not be the optimal solution if you're interested in other varieties. And we do not know what would be the most general situation to consider, yes. What about higher dimensional rationally connected varieties, etc.? Okay, so this implies representability. Okay. Now that you know that it is representable, all the procedure that we've done, looking at the birational map to P3, etc., and writing the equation star that is here, you can, instead of applying it to x over k, you can apply it to xk bar over k bar. And in this case, the curves Ci are smooth curves. So their Jacobians are abelian varieties. And this shows that the identity component of my intermediate Jacobian is a direct factor of an abelian variety, hence an abelian variety. It's a direct factor of an abelian variety, hence an abelian variety. Because Jacobian of smooth projective curves are abelian varieties. Now the statement about the polarization, I'm not going to say anything, but we need to construct a principal polarization on CHO2, and it's going to be induced by the principal polarization on these Jacobians of curves. So the required polarization may be built over k bar from the principal polarization of these Jacobians of smooth curves.
But how do you check that it is independent on the rationality construction?
Yes, so that's a very good point. It is very, so and it is at this point, yes, that's very extremely important. So when I stated the theorem here at part 4, I said that it carries a canonical principal polarization, and I didn't tell you what I meant by canonical. But I should have written a precise and longer statement that tells you, that gives a characterization of this principal polarization. That tells you it satisfies this property and in a way that it characterizes theta x uniquely. And then I would check that the principal polarization that I construct using a rationality construction satisfies this characterization, hence is the unique one. Would you want me to do that, like to write down the characterization of the principal polarization that we use, or?
No. It's enough to know that it exists.
Yeah, and it is of course very important to have this characterization of the principal polarization for it not to depend, as you say, on the rationality construction. Thank you. Where was I? No, sorry. I need to go back here. Okay. Okay. So, and the only thing I think that really remains at this point is to prove the obstructions to rationality. Like the other assertions quite follow. What we need to do is prove the obstructions to rationality. And if the base field is perfect, it is clear. Because just because of the formula star in blue that is at the top of the slide, you see that if K is perfect, then this the group scheme that is the kernel of F lower star, you call it G. Then the group scheme Z, I mean, you notice that it is the Picard scheme of P1 if you want. And so really you have realized the CHO2 x over K as a direct factor respecting principal polarization of a product of Jacobians of smooth projective curves over K. Oh, sorry. Shows assertion 5, that is the obstructions to rationality, that is the fact that show 2x over k is a direct factor of Jacobians of smooth projective curves. Okay, and if K is imperfect, the argument doesn't totally work because the Ci that you have to blow up to go from P3 to X, they're regular curves, but they may not be smooth. So you run into the difficulty that the curves that you blow up, if you look at them over the algebraic closure, they may be singular, they may even be non-reduced. And so, I mean, their Picard scheme, the connected component of identity is not even an abelian variety. It has a linear part, a unipotent part. And so just looking at equation star doesn't prove 5, where you really need like Jacobians of smooth projective curves that are the principally polarized Jacobians that are abelian varieties that we are used to. And the miracle that happens is that, so if you look at this equation star, some of the Ci, some of the curves will maybe not be smooth, will be only regular curves that are not smooth. So maybe the identity component will not be an abelian variety. But then for these curves, they will not contribute to show 2x over k. They will all contribute to G, to the kernel of F lower star. So this is, if k is imperfect, you have to check that the curves that are not smooth, they do not contribute to show 2x over k. And it is a very non-trivial fact that you have to prove. So let me erase it.
But Olivier,
Yes.
Imagine that your x is just the blow up of P3 along this curve. So that
yes.
you don't have any contraction. Then how can this
you do have a contraction. Let me show the diagram again. The diagram is this one, so I'm sorry it's not very beautiful. But you start from P3 and Y1, that is Y1, and you blow it up successively. You get Y2, Y3 up to Yn plus 1. And then there is a very big contraction that you know nothing about, that is F, and that goes to X.
No, I mean, just let us consider variety X, which is the blow up of P3 along such a curve.
Yes.
Then its rationality construction is just a single blow up with no contraction.
Yes.
And then how does this bad part of the Jacobian of this curve can go away?
So the point, and I so okay, let me call this variety X tilde. Okay. The point that I was hiding is that X tilde in general is not smooth. Of course, if you blow up smooth curve, X tilde is smooth. But if you blow up regular curves that are not smooth, then X tilde is not smooth. And if you look at it over the algebraic closure, it's badly singular.
Okay, I see. Mm-hmm.
And so it means that in the proof, to run the proof, you need to consider these varieties that are not smooth as intermediate steps.
Okay.
Thank you for the question. Thank you.
But doesn't that introduce an additional complication with the use of Thomason's formula? Because if I remember correctly, Thomason's formula requires that the locus being blown up is regularly embedded.
Absolutely, and this is exactly what we have. you have to absolutely, it's blow up along regular immersions, and we need this generality. And this is exactly what happens. Basically, because it's base change of inclusion of regular scheme inside a regular scheme. And this is a...
Okay, so the hypotheses are still satisfied because of that.
Yeah, and
even though the ambient space is singular.
Yes, and we are very happy that K-theory has been developed in a sufficient generality by these people. Okay. Okay, so I go back here. I'm just going, and then I will stop, I think. I will just state the miracle that you need, and that is true if K is imperfect, which is the fact that those curves that are not smooth do not contribute to show to X over K. So if K is imperfect, I mean, in general, then F lower star of peak 0 Ci over K is 0 if Cy is not smooth over K. So hence, the only curves contributing to show to X over K are smooth, and this proves 5. Okay. So really what happens is that when you look at the birational morphism from X to P3, to resolve it, you need to blow up many curves. Some of them will not be smooth, but their contribution to Cho2 will be killed eventually by the contraction F, automatically. And okay. So, and this is verifying this is the hardest part of the proof, and it's not necessary if you're only interested in perfect fields. And I think, yeah, I'm going to stop now. Thank you very much.
So I had a question about about comparing your Chow2 to another construction. The other functor-ish that I can think of that would describe codimension 2 cycles is the motivic cohomology H42, which of course is not the same kind of object, but I was wondering if you could compare the two in any useful way.
So, you point out two things. The first is that there are many variants of the functor that we could have used. So you point out one, which is motivic cohomology, but there are others like cohomology of Milnor K-theory sheaves, H2 of K2, or Fulton's contravariant Cho groups. And the reason we choose K-theory is that the theory is very well developed in a great generality, and it applies and so we have all the basic theorems we need were proven by Thomas Homsey. And as for motivic cohomology in particular, the problem is that it is not developed in the generality we need. We really need integral coefficients without inverting the characteristic, without inverting P in the coefficients. We need
that would be a problem.
Over imperfect fields. It's just not developed in this generality. But okay. I agree with you that morally, this is the correct definition, motivic cohomology, of course. I agree with you.
Mm-hmm. Now, if you were to work in characteristic 0, can you compare your construction in that case?
With motivic cohomology?
Yes.
We did not,
I guess you still have problems with the coefficients of motivic cohomology not I'm not sure if it's known with integral coefficients, the facts that you need, even in characteristic 0, I think that might be known. I'm not sure.
No, I think in characteristic 0 we could build a functor. I'm trying to think. I don't remember if it was motivic commutative. I don't think so, but there are difficulties. There was maybe if my collaborator is here and has something to say. I remember that there was one particular other functor that we did not manage to compare with ours. So there are difficulties to also compare functors in general, but then of course, if you're in the case, okay, for all functors you can think of, and that for all functors you can think of and that are moderately developed, in the case of k-bar rational varieties, they will all be represented. I mean, if they're, you see, it's if you know how to compute projective bundles and blowups, then you will be able to show representability just as I did for K theory.
Mm-hmm.
But maybe you will not be able to compare the two functors for other classes of varieties, say rationally connected threefolds.
Mm-hmm.
So for instance, in characteristic 0, comparing a functor built on K theory and built on motivic cohomology, I don't know if we would know how to do that. It would, for general rationally connected threefold, I guess it would be a theorem.
Okay, thank you.
Hello, Olivier. I have a question, if I can.
Oh, hi.
Hi, I'm happy to see you. So in the beginning of the talk, you mentioned even in the complex case, the existence of a universal two-codimensional cycle. And if I recall well, in the works of Voisin, this is connected to stable rationality rather than to rationality. So my question was, I mean, I don't know how it works with other fields, but how, I mean, the examples you constructed, are they stably rational or not? I mean, the examples where you have on a lift, on the algebraic closure, they are rational. So how does it work?
So this is a very good question. And the answer is we do not know. So for instance, so we have concrete equations of the examples. I wrote one for theorem 1, and in theorem 2, or 4, I didn't write concrete equations, but we have. And in these cases, we do not know about stable rationality. And it should be thought of as exactly the same situation, I think, in my opinion, as for cubic threefolds over C. Like Clemens-Griffith shows not rationality, but we today know nothing about stable rationality of these cubic threefolds over C. I think for all the examples I've talked about, it is the same situation. Clemens-Griffith or variance thereof disprove rationality, and I know nothing about stable rationality.
Okay, so even knowing rationality over an algebraic closure does not tell you anything about stable rationality.
That does not help me at all. No, I would be extremely curious. I mean, they're concrete varieties, like we have equations. It's a concrete question. I don't know.
Okay.
Very good question. Thank you.
Thank you.
And may I ask, maybe I just missed it, but so you explained that you construct an abstraction to rationality, but then to show that something is non-rational, one has to check that the abstraction is indeed non-trivial.
Yes, absolutely.
Maybe I just missed it. How do you do it for instance, in your intersection quadratic example?
So indeed, I didn't explain it at all. But because it was a little, I don't know how much time it is.
Well, we're still fine. We're not missing the last bus to go home from home. Well, anyway, maybe you can give just a hint. So maybe without particular calculations, maybe you can just give an idea how to.
Yes. So the point is that in concrete examples, okay, let me go here. Okay, in concrete examples, to apply the main theorem, you need to verify that there is indeed an obstruction. So you need to compute, in some sense, the group scheme show 2x over k, and let me compute. Let me say what we need to know in the case. So. Where X is an intersection of two quadrics in P5. Then what is so to have X over K that you need to compute to disprove rationality? Well, I mean, we know well the codimension 2 Chow groups, say, over the algebraic closure. And I mean, this tells you that the Néron-Severi group of codimension 2 cycles is just Z, given by a map that I will call delta, that is given by the degree, really, of a codimension 2 cycle. And so what you need to know is that are geometric informations, really. So if you take F to be the variety of line, of X, then, I mean, lines are degree 1 codimension 2 cycles. So there is a natural morphism going from F to, well, delta minus 1 of 1 that just associates to a line over K bar, associates to a line. Its class in the Chow group. And this turns out to be an isomorphism. All what I'm writing is completely, is very well known. Say, if you, at the level of K bar points, say, this is a bijection of K bar points, and you have to verify that it gives rise to isomorphism of schemes between here the variety of lines and one of the components of my scheme Chow 2x over K. And you can do the same with the variety of conics. And there the geometry is a little bit more complicated than what we would need, and that is also very well known at the level of K bar points, and that we need scheme theoretically using our definition of Chow 2x over K, is that, so of course a conic, I view it as a degree 2 cycle. It has a class in the Chow group, so it lands into delta minus 1 of 2, and it's the image, it's not injective, and the image I call D is a smooth projective curve of genus 2. And this inclusion identifies delta minus 1 of 2, well, with the Albanese of D. I can also write pick 1 of D. And as a consequence, since delta minus 1 of 2 is a principal homogeneous space, it is a torsor under my intermediate Jacobian. Well, my intermediate Jacobian is going to be pick 0 of D. Okay, so and so all this, to prove all these facts, you can actually go to the algebraic closure, prove them over the algebraic closure, but over the algebraic closure, all the varieties we look at are rational because over the algebraic closure, and so you just have to analyze actually blow-ups and you have formulas for blowups. So this is how you prove and now you have a lot of information on the Cho2x over K. You know the identity component. It's the Jacobian of a smooth projective curve of genus 2. You know the inverse image of 1 by delta. It's the variety of lines. You know the inverse image of 2 by delta. Well, it's the Albanese of my smooth projective curve of genus 2. You have a lot of geometric information, and you need to reach a contradiction if X is K-rational with assertion 5 in the main theorem.
And maybe another related question. So if the field was algebraically closed, say complex numbers, then there is an industrial method of distinguishing intermediate Jacobians from Jacobians. So when you have a structure of conic bundle, then you can deduce everything from the theory of prime varieties, right?
Yes.
And do you have an analog of this? So you started with an example of a conic bundle.
Yes.
Can you do some kind of prime variety there, or at least its analog?
Alors, so the first example I gave, that was a conic bundle that you mentioned, can be interpreted or viewed as a degenerate example of prime variety, indeed. But we do not use the theory of prime varieties. But I agree with you that it can be, if you know the theory of prime varieties and you look at our examples, you understand it better. A difficulty of writing down a general theory of prime varieties in this setting is that we can only work with K-bar rational varieties so far.
Well, this means that possibly you, so it means that the examples that could, in principle, can have a chance to be related to prime varieties are like geometrically rational conic bundles, which in turn means that when you pass to algebraic closure, they either stop being standard, like become non-minimal.
Yes.
Like in that example, or maybe just the prime varieties are covers of some very special curves. So you just anyway, you mean that there is no analog of this theory yet?
There is probably an analog, but since we are restricted to K-bar rational varieties in the work we did, I mean, we don't, we cannot. Let me say something. So for K-bar rational varieties, we have this theory that I think works well. Okay. In general, if you look at K-bar rational, if you look at rationally connected threefolds, one thing that we do not know how to do is to construct a principal polarization on Moore's intermediate Jacobian. For rationally connected threefolds, Fano threefolds, we do not know in general how to construct a principal polarization on Moore's intermediate Jacobian. But for prime varieties, you can, because on prime varieties, there is a, you know how to construct the principal polarization. And so this is one way that prime varieties behave better, that you have for free the principal polarization that you need on the intermediate Jacobian.
Possibly problem is with non-minimality. It can be non-minimal of algebraic closure, right? And
apparently there are many
you will have difficulty with in constructing prime variety.
Oh,
You have no
yes.
double cover.
That's why I said that it was a degenerate case. There is a double cover, but it is not. It is connected, but not geometrically connected. It's
yes.
So it's a degenerate case of prime variety. So yeah, it's not the classical setting of prime variety, but you can, it looks really like a prime variety.
And another question, even less relevant to the talk, and is it possible to do part of this theory? So suppose that instead of considering arbitrary fields, you stay over algebraic closed field, but add some group action, some geometric group action, like finite group, for instance. Do you have at least a feeling if some of this can work?
So I have not thought about it. So you mean to distinguish?
Well, to abstract G equivalent rationality construction.
Yes. Let me. This is a very good question. I have not thought about it, and I'm not so familiar with this G equivalent rationality problem, so I don't want to. So you mean there would? Okay. So you mean obstructing by looking at an intermediate Jacobian together with an action of G? It's very interesting.
Something like this.
It's a very interesting idea. I've not tried, and so I don't know. But it looks very interesting idea. Yes.
Okay. Any more questions to Olivier? So it seems that there are already many questions. So let's thank Olivier.
Thank you very much.